Everybody's back in the swing of classes and thinking about upcoming midterms, so we're going to look over the next few weeks at several ways that you can integrate MetPy into your classroom to solve different kinds of problems or demonstrate concepts. This is great if you're a professor teaching courses or if you're a student that needs deeper understanding of something you're having trouble with. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. You know, we often talk about MetPy as a great tool for research, which it is, but it's also a great tool for teaching or just checking or refreshing your general understanding of the concepts that we've come to rely on every day as meteorologists. So over the next few weeks, I'm going to do some problems ranging from thermodynamics to dynamics to radiation and climate. And we're going to look at how to solve some of these using MetPy to help boost our understanding by being able to do a lot more than we could just with pencil and paper. Generally, it's not so much about being able to do the algebra, it's more about understanding the concept and getting that intuitive feel for what the equations are trying to tell us. So this week we're going to look at a few simple problems that help us understand potential temperature better. So what is potential temperature? Well, potential temperature is the temperature that a parcel would have if it is dry adiabatically brought from one pressure level to another. Commonly we use 1,000 hectopascals as the reference pressure, but it doesn't have to be. We often denote potential temperature with a theta. So our problem here is we're on a conference and we're going via air at a height of 30,000 feet. We're going to assume a standard atmosphere. We want to know what the outside pressure is, what the outside temperature is, what is the potential temperature outside of the cabin, and then assuming that the aircraft is pressurized to about 750 hectopascals inside the cabin, what's our cabin altitude in feet? And if we just took that outside air and compressed it to put it into the cabin at that 750 hectopascals without any temperature, heat exchange, anything like that, what would its temperature be? This may look like a relatively daunting set of questions. We've got 5 things here, but as you'll see with MetPy, it's relatively straightforward. So first, since I want to make this as generic as possible, because I may want to play with different variables, I'm going to set my height as a variable 30,000 units dot feet, and as soon as I type that dot, triggers in my mind, I need to do some imports because we're not going to know what units are. I'm going to import metpy.calc as mpcalc, and from metpy.units, I'm going to import the units registry. And now we can create that variable. So what's the pressure outside the cabin? That's the first question. Well, luckily for us in MetPy, we have a height to pressure standard atmosphere function. And if we look at the documentation, it says it uses the NOAA 1976 standard atmosphere, and we give it a height. So I will pass it my height. And then we're going to print a complete sentence because that's how we answer questions. We use an F string. The pressure at height in a standard atmosphere is pressure, and I'm going to specify that though it's a float, I don't want anything after the ones place. So the pressure at 30,000 foot in a standard atmosphere is 301 hectopascal. We've answered that first question. And it may seem silly to go ahead and put the answer in a complete sentence, but one, it's better than printing out just numbers all over your notebook and you don't remember what they are. And 2, if you think about a discussion with somebody or your qualifying exams or even a test, you don't just spit out an answer. You have to give the context with that answer and generally form a complete sentence. So there we go. That's why we're doing that as a complete sentence. Now, what about the next portion, which is what's the temperature outside? For that, we need to look up the lapse rate for a standard atmosphere, which I did, And in the pressure range that we are in, the standard atmosphere is minus 6.5. And then we're going to add units of delta, remember, delta degrees Celsius, per kilometer. That's our lapse rate. The starting temperature, again, I'm defining these as variables so that I could change them if I want to and just rerun the notebook. That's going to be 19 degrees Celsius. That's standard atmosphere starting conditions. So what's the temperature at altitude then? Well, the temperature at altitude is my starting temperature plus my lapse rate times my height. And we let MetPy's units deal with the fact that a lapse rate's in delta degrees Celsius per kilometer and our height is in feet. It can take care of that. And now we print our sentence again. The standard temperature at height is temperature. And again, we don't need anything past the decimal point. So minus 40 degrees Celsius, pretty cold. All right, next we need to find the potential temperature. Again, luckily, we can calculate this with MetPy relatively easily. Potential temperature. And of course, as a student, you'd be going and looking up these equations. But if you wanted to make more plots or be able to just play with some of these numbers, say, okay, what about 20,000 feet? Or what about with different than standard conditions? This lets you do that in a much more quick way to get that intuitive feel. So this isn't a way to just make your homework go faster, but it's a way to check your understanding of the concept. And it looks like we need a pressure and temperature, both of which we have now. Okay, the potential temperature at height and our temperature is potential temperature and looks like we have a period misplaced there. All right. 328 Kelvin. That's great, but I would prefer it to be in the same units. So we'll go with Celsius. And that's a potential trap that I see a lot of people fall into because we see that we're getting an unmatched parentheses issue. That's not actually the root cause. It's that we have single quotes inside single quotes, so it doesn't know how to pair things up. So we need to use double quotes there. All right, so 55 Celsius is quite high potential temperature, really. That's maybe a surprising number even, considering that we're at minus 40 at altitude. All right, so what next? We need to calculate the cabin height. We know the cabin pressure was specified as 750 hectopascals. So our cabin altitude is going to be pressure to height standard. And we see that takes a pressure based on standard atmosphere. So our cabin pressure. Print out our sentence. The cabin altitude at cabin pressure is and if we print that out, we see we get a lot of decimals that we don't need, and it's in kilometers, but our altitude's in feet. Remember our double quotes here. So I want it in feet. And now we see 8,087 feet. So relatively low cabin altitude, far below where oxygen is required as even a crew member or a passenger on an aircraft. But now comes the most interesting part of the question. We're taking that outside air and we're compressing it using a turbine on the airplane and injecting it into the cabin. That's how we're pressurizing the cabin and getting fresh air in. Now we know that potential temperature is a conserved quantity. So what would be the temperature of that air as it's injected into the cabin at 750 hectopascal from the outside after we compress it? We know that compressing air involves putting work in and is going to increase the temperature. So our gut check says this should be a higher temperature than minus 40, and that 55 is going to be the number that we would have to conserve in terms of potential temperature. So I'll call it our unconditioned air temperature. And that is going to use the temperature from potential temperature function. Now again, we can do the algebra and rearrange things. That's a good exercise. But we can also now use this to enhance our understanding. I'm going to take the cabin pressure and the potential temperature. So it says, take the potential temperature that we calculated and now see what the actual temperature would be at our cabin air pressure. So the injected cabin air would be unconditioned air temperature. And let's make sure that's an F string. And we get a result in Kelvin. Let's go ahead and take that 2 degrees Celsius. 29 degrees Celsius. If you think in Fahrenheit, that's 84 degrees Fahrenheit. So we would be having very, very hot air injected. And in fact, the air that's being compressed by the engines on a passenger airplane does go through a series of heat exchangers to lose some of that heat to the atmosphere so that we get a nice, comfortable cabin air temperature. But it's pretty interesting that we do have to actually lose heat from that air because potential temperature is conserved, and we're taking that lower pressure air, putting work into it, and injecting it into a higher pressure cabin. So I hope that you found this useful and that it helped aid your understanding of potential temperature. It's a great notebook to play around with because now it's very easy to say what happens at 20,000 feet. Well, that injected cabin air now is down to 61 degrees Fahrenheit. So that's quite a difference for only that 10,000 feet. Or what happens if my lapse rate is steeper or not as steep. These are all great things that you can play with. I hope that you found this useful, and I'll see you on next week's MetPy Monday.